Okay, as I promised in the last video, I will now show you how to actually carry out a linear elastic FE analysis on the same load and what are the key differences. Just to be sure, I will now save this in a separate folder so that the results can be compared. So linear elastic and fixed. So this is now the type of analysis is what we will be learning. We'll be learning, or what we'll be doing is a typical FEA. So I'll just rename it as well just to avoid any confusion. It says, do you want to copy the result file? I mean, it may be a good idea to later do it, but compare it side by side. So I'll not copy the actual result files to the other saved version. Right, so I'll just do this, and now what I will be doing is I will be actually going back into my simulation, and I will be actually, I can either edit this or I can just do the whole as a new study. And so this is what I plan to do. So what I will be doing is I will be I think what will be simpler will be that I just delete the study and reapply everything, or I can just go here and copy my study. Okay, and I want to use some of the features. Okay, probably that's a bit problematic. I think I was able to do that with different software, but maybe not here directly. Okay, so what I will be doing is I'll just say new study, and instead of buckling, now I'll choose static. So I'm just going to start everything from the scratch really. So I'll just go into the static, and I will call it as static FEA strut. Okay, uh, fixed. Okay, so with this, I don't really need to select any other options, so I'll just say okay. So now I've got a new analysis here in this case, and I can just save everything to be sure. And we'll see if okay, materials. We'll use the same material as the last time. So we'll use the custom material that we added, right? So that's it. So we apply the material. So once I've applied the material, I can now again define my boundary conditions. So my boundary conditions will be defined in the same way. So on the top edge, I will be using this split line to actually ensure that I get my part to be in a pin condition. The reference plane again, I will be using the same reference plane, front plane mid, right? So there's nothing changed in as far as these things steps are concerned. Again, I will be constraining it along this length axis. Okay, you can see from the arrow, as well as I will be constraining it along normal to that axis, but not along this length. Okay, so two axes I'm constraining, and the third I'm keeping free. With this, that's it. Now going back to the other side, we will now apply fully constrained boundary condition on this edge, uh, as well as this face, and then this edge, this edge, this edge, this edge, and this edge, this edge. Yes, so all the edges and the faces, but like I said, you don't really need to do that. You can just even select the face. In this case, it will not make much difference with the results, but let's just do exactly what we did in the previous case. I'll go into the fixtures, go into fixed geometry. In this case, I don't have to go into advanced. I'll just say okay, and it will automatically constrain all those edges for me, and as well as the faces. So now our boundary conditions are done, so we can easily apply the load. And in this case, I will actually be now applying an external load in the form of a force. So that force now needs to be what was my buckling load. So that was around 17.46, if I remember correctly. Okay. So I'll just apply that. In fact, what I'll do is I'll go slightly above that just to demonstrate that actually even above that what will happen as per our linear FE analysis. So let's apply 17.5 newtons, slightly a touch higher than what we had. And again, I will be selecting this full phase 1 as well as full phase 2 that I will be using for applying this load as a compressive load, and I will apply it as a total quantity, okay, rather than per item of those two phases. So the total force is 17.5 newtons now on the top force phase, and I will just select OK. Now with this, our basic model setup, material and boundary condition is complete. I can now actually go and run the analysis by creating a mesh. So I will create a mesh, and again in the start I will actually keep it same as a standard mesh, although in this case, as I will show you maybe later, that the actual selection of the Jacobian points as well as the coarseness of the mesh will have some effect, although not a huge effect, but still it will have some effect because now this is a linear elastic stress analysis. So I will just run it, and now you can see it is a still fairly reasonable mesh. I can now actually run this study, but if you want, you can actually first of all define the output parameters, but I would like to do that after I've run the study. Right, so I've now run the study, and you can see here some of the key parameters. You can see here there is no sign of buckling as far as the deformed shape is concerned, right? You can see here now that we have plotted the displacement, and the software does not know that the strut would have actually buckled by now. So software believes that for as far as the stress is concerned, the one yield strength, which is 8.5, is into 10 to power 8 is actually much higher than the highest stress in the part, which is right now 4.03, and majority of the part anyways in the middle is even lower in 3.12 megapascals. So that means this linear elastic analysis would have actually misled you to believe that this rod would be completely safe. And this is a key point whenever you are doing this analysis, that you first do the buckling analysis whenever you expect that the object can buckle, and that will then allow you to see whether later on if the results of your linear elastic analysis are meaningful or not. I can, if you want, I can plot other components like the actual sigma x component, for example, or the sigma y component, for example. In this case, sigma y would be the most significant one. So let me just plot that first of all. So if I just add one stress, so I just define stress plot. Okay, and I just want to plot along the y-axis, and I want to use megapascals as my unit. Okay, and I can just use the deformed shape in the true scale as well. Okay, and you can see here that in this case the stress values are compressive, so it's minus 2.608, which will be somewhere around this place where it is constrained fully. And then you can see that most of the part, if you probe it, you can actually see that the stress values, for example, in this region is around 3.279, which is somewhere here in this scale. And this is obviously much more lower than the yield strength of the part. So with this, I come to the conclusion of this part of the exposition. Now, obviously, you can plot other values, you can plot strain values, but you can see here that how FE analysis can also be misleading in such cases. So standard static analysis, that is, but you need to know basically what you're trying to simulate. One word of caution is that the approach that I've shown you for the buckling analysis previously also has limitations, and it will only work if the buckling analysis is carried out on a linear elastic. Sorry, it's in, yeah, will if it is carried out on a strut that will behave as an Euler column rather than intermediate length or short length column. So there, of course, the different equations and different methods will need to be followed. Thank you.